Hello, everyone. Thank you so much for joining us. My name is Jason Montgomery. I'm your moderator today, and the live session that we'll be covering here is where is high-density computing at in 2020? And this session is brought to us with On Semiconductor. Let me tell you about our presenter from On Semi, and we'll hand it over to him. Our presenter today is Leo Chow. He's a senior marketing manager in the Cloud Power Group at On Semiconductor, and he focuses on product development on multi-phase power regulator solutions aimed for high-power CPU. In the past, he's held positions in field applications engineer and management to support system-level designs for customers. He obtained his BSEE from the University of California, Davis, and his MSEE from Stanford. A couple of reminders for everyone here. We do have that Q&A box that's down at the bottom of your screen, which will allow you to submit questions to Leo live during this session, which we'll cover in a live Q&A session afterwards. And with that, Leo, I'll hand it off to you for the presentation today.
Thank you very much, Jason, for the introduction. Hi, everybody. My name is Leo, and the topic that I want to talk about today is on high-density computing. With the focus on the power supply and voltage regulator technologies that we are at On Semi consider as the core technology of our business. And so today I want to talk about some backgrounds on why high density computing is needed, what the industry trend is, how we at On Semiconductor are going to do to address the higher density in a computing power, and some of the challenges that we're seeing, as well as what approaches we're taking to address these challenges, and what we see is the future trend. Okay, a little background on why high density computing is needed. Why we need to increase the power density in the computing and server application. So this chart shows the trend. Basically, it shows the trend of growth in the server market. In the dark, going from 2015 to 2025. In a brown, so the brown box shows the user hosting, and what that means is these are customers and users that actually host the cloud. The server internally within house, and the light blue squares show the provider hosting. So this is basically an indication of cloud, where the users are not actually storing data in their local server, but instead transmit the data to a cloud server, for example, like Amazon or Microsoft. So basically, you can see from the chart that the growth is tremendous, especially in a cloud server area where the growth is pretty much exponential, and this paves the way to needing higher and higher power density to be able to support the kind of growth that we're seeing on the market. So this is the chart of a historical Intel CPU performance, and you can see the trend going from all the way back from 2006 to this doesn't show the latest, but it tops out at 2017. But you can see that the trend is not just linear; it's exponential. The CPU, so with the technology in the digital, with the digital technology and Intel's effort, both Intel and actually AMD's effort to reduce their pitch to now I believe they're at 7 nanometer. They're able to improve their performance exponentially. So compared to 2006, the Skylake CPU in 2017 has 41 times the performance. So it's and that number is still going up. Here I provided a chart of the peak CPU current for each generation of the CPU dating back to about 2010. So it's we started with the Sandy Bridge CPU in 2010, moving to an Ivy Bridge, Haswell, Broadwell, Skylake in late 2017 to 2018, to what's called a VR13HC, codename Ice Lake for the CPU, to now now Sapphire Rapids for Intel's VR14. So you can see that the trend started off kind of flat, but goes obviously exponentially more. In 2010 to 2012, for the Sandy Bridge and Ivy Bridge CPU, we're just at about a little over 100 amps as the peak current for the CPU. That increased to roughly 200 amps for Haswell and Broadwell, and it just took off, starting in the Skylake CPU generation. So Skylake is about 228. Ice Lake almost doubled that to about 400, and Sapphire Rapids, which is where we are right now, is peaking at about 550. So part of this exponential growth is also Intel's response to AMD's competition from AMD, who is aiming to have a bigger pie in the server CPU market. So Intel is leading the 7 nanometer effort, and Intel is obviously playing some catch up right now with the Sapphire Rapids. So with this, what are we going to do within our team and company to be able to address such a rapid increase in the low current? And below, I will highlight some examples in evolution of what we have been doing for the last decade. So here I am showing a typical multi-phase Intel CPU VR design. So on the right, you have the CPU itself, which is the load. On the left, you have the controller that's basically issuing different PWMs and clocks to the FETs themselves to be able to switch on and off. So this is a typical buck converter topology where you have a gate driver, a controller controlling the gate driver, a high side FET and a low side FET, and an inductor. The goal of this topology is to be able to do a step down in voltage that typically is going from 12 volt down to the CPU voltage, which has been changing in different generation. The core voltage has been sitting at about one volt and below, depending on the power state of the system. So if the system wants to use a lot of power to process network traffic, they will boost the core voltage to about 1 volt. But if it's not seeing much traffic, it may throttle down and reduce the core voltage to say a 0.8 volt or even 0.6 volt. So this voltage regulator provides that step down voltage to that is a very provides a very steady step down voltage to power the CPU, and the goal is to be able to supply the power to the CPU even when there's a large load spike with a very steady output voltage. So what do we do with the power supply in regards to the FET technology, the actual power component, which is the gate driver, the high side FET and low side FET. Originally, dating back to a decade ago, we would design the power this voltage regulator with a discrete gate driver, a high side FET and low side FET. In each one, the high side FET and low side FET are typically around 5 by 6 millimeter. Gate driver maybe a little bit smaller, like a 3 by 3. So this is what we used to do about a decade ago, and this is basically the largest solution that at the time, or considering what we have now. This solution area is definitely much larger than what we have now. So the next technique to reduce the footprint and the solution area and increase the density is to combine the high side and the low side FET into one 5 by 6 package, but still have the discrete gate driver. Some vendors have the gate driver built into the multi-phase controller. Some have them as discrete, so it just depends on the customer's preference. Okay, and this way we basically combine two components into one while staying with the same package. So this would almost double the power density. So as the low current continue to go up and we need to add more phases to the voltage regulator, what else can we do? The next step is to obviously to combine the gate driver and the high side FET and low side FET all together into one 5x6 package. And there may be people wondering why we don't just put the gate driver inside the multi-phase controller. And there's a good reason for that. It's because the routing on the gate driver going from the controller to the gate driver itself is actually very important, because it does carry the drive current that's going into power to turn on and turn off the high side and low side FET. So these traces are relatively sensitive on the board, and we have to be careful routing them away from noisy areas. Otherwise, we would get into all sorts of issues. So a better way to do this is to actually put the gate driver inside the same package as the FETs themselves, so that we can keep these routing small and within the package and away from the noises. And the signal that's issued by the controller to turn on the high side and low side FET is just a simple clock signal, which is a digital signal with a logic high and logic low. So it's relatively noise immune, and that is why the industry has taken this approach for the last few years. And another reason to integrate all of these is so that we can keep all the important components inside the same package to keep the parasitics small. Because if we come back to the very original solution, you have this big solution sitting on the board, and you have all sorts of routing and parasitics that can potentially increase the what we call the switch node ringing. Basically, this can be very destructive to the FET if the ringing amplitude gets too high. So each FET comes with a breakdown voltage rating. So we definitely do not want to exceed that. So by combining the different components into the same package, we're able to minimize the parasitics, inductance, and resistance inside the package, so that we can keep the switch node ringing small. Okay, here I am showing a typical cross section of our power stage. Sorry, by the way, we call this the power stage, where we combine the gate driver, high side FET, and the low side FET together. It's called a power stage. So here is a typical cross section of a 5x6 power stage. On the left, we have a driver IC. On the right, we have the high side FET. And here you can't see it, but the low side FET is sitting below this copper clip. So we use the copper clip to connect the high side FET and low side FET, and this basically becomes the switch node that goes out to the board and to the inductor. The junction is the node between the high side FET and low side FET. And on the driver IC, we actually the job is to not just turn on and turn off the low side FET, but we have in our new generation of power stages, we have incorporated a few smart technologies into our driver with several different features. One of them is to provide a current output that can go back to the controller. So basically, this represents how much current the power stage is drawing or supplying to the load. And each phase of the power stage is going to report this differentially back to the controller. So the controller can know how much total current is drawing and how much per phase current, how much current each phase is also drawing. And there's several functions inside the controller to be able to balance the different phases, so that balance the currents between the different phases, so that we don't have one phase carrying more current than the other, which can also spell trouble. And also the current reporting also gives the controller a sense of what the total output current is, and so that the controller can prevent an overcurrent event. So it can perform several functions, either to latch off the output when the current limit is reached, or it can do a hiccup function to continue supplying the current, but not let it exceed the maximum current limit. Another good feature that the power stage provides is what we call T-mount, basically a temperature monitoring output. So each phase is going to report a voltage, report the temperature in a form of voltage. That is there's a scaling factor that basically translates the temperature into a voltage. So on the board, this T-mount are all tied together. So whatever phase is at the highest temperature will override the bus line. So the controller knows the highest temperature of the power stage, and is able to perform an over temperature protection mechanism. So that we don't allow any of the phases to exceed a predefined threshold on the temperature. For example, like 100 degrees C or 120 degrees C. But internally, the power stage itself also has an internal overcurrent protection, over temperature protection, and also high side short protection. So these will kind of act as a secondary protection level on top of what the controller defines, basically to prevent catastrophic events. Okay, here I am showing a product portfolio that the Cloud Power Group offers. So we mainly have a 5x6 package and also a 4x5 package that's aiming for lower current. So you can see that the current basically goes up as we move up. The 5075 and the 5076 are both the 4x5 in a 4x5 package. They're rated at about 20 amps and 35 amps. And the 3172 is rated at 55 amps. 3170 at 70 amp and 3180 also at 70 amp, but it does use a better effect technology to have a better efficiency. So does the 5062 and 5071. They're rated at 70 amp and 90 amp respectively. So we basically offer a wide range of portfolio to support the power at a different load level. The highest power products like the 5071 and 5062 will probably be targeted for the VCCN core rail on the CPU. The lower current parts will target the peripheral rails on a typical server and data center design. And these parts are all in production. We are working on next generation products that will have even better efficiency and features. Okay, so with this, there are definitely still challenges that we're facing. Here I'm listing only 3, but this is obviously not everything that we see, but these are definitely the most important ones. So again, going back to the slide number 2 and slide number 3, we are seeing an exponential increase in the CPU load, and what that translates to is we have to keep adding more phases to the power supply. So within the last 10 years, we're seeing the number of phase counts to double. However, the CPU current actually quadruple. So what does that mean? That means we have to increase the peak current rating for each of the phases. And later on, I'll have a slide to kind of to quantify the numbers. And of course, the larger as we go up in phase count, we obviously have more components, and the total solution area is going to keep growing and growing. And what that means is we have to start putting the solution farther and farther away from the load. And with that, there's there's going to be an increase in the parasitics on the board, which translates to more power loss. Okay, so this is a similar diagram that I showed earlier, but it's looking at the per phase current that needs to be supported instead of just the total current. So very similar trend where we stay somewhat flat for the first few years, and then we see an exponential increase. So from the Sandy Bridge and Ivy Bridge generation, the number of phase counts were around 3 to 4, and trying to support about 100 amps. So the per phase, the peak current per phase is right about 25 to 30 amps. Going to Haswell and Broadwell increased by a little bit, not much. Going to Skylake, we're going up to a 5 to 6 phase design, but the current doubled to about 228. So per phase current is sitting close to about 40, and it just went crazy as we entered the Ice Lake CPU generation, where we had about 400 amps of total CPU peak current, but only 7 phases. So that translates to about 56 amps per phase. And in this generation, the peak current is about 550, but the number of phases only went up by 1 compared to Ice Lake. So we have to support 550 amps with an 8-phase design. And if you do the math, that puts us right about almost close to 70 amps per phase. So you can see that just from a few years, over a decade, we're asking the power stage and effect technology to be able to support just 25 amps to now close to 70 amps, almost about 2.5 increase in the peak current. Of course, nobody's power stage can support 70 amps DC like in a typical server environment. So these are kind of like short bursts for a few milliseconds, while the CPU needs to provide the necessary current for just those few milliseconds to support a drastic, like a short spike of network traffic. Then it will back down. But still, we need to be able to supply that current for some amount of time. Okay, so with this, what are we doing, and what can we do to make sure that we can address the demand from the market and the CPU without compromising quality and reliability? So one of the things we can do is very obvious. So we can make better FETs. So here I am showing our FET generation dating back to 2002. And this is actually part of the Fairchild acquisition. So these numbers, these nomenclatures, PT3, PT4, down to PT11 are actually Fairchild nomenclatures. So all the way back from 2012, we started with PT3, going to PT4, PT5, PT8, PT9 to now PT11. And with each generation, we're able to improve the FET technology to either reduce the RDS(on) or the switching losses, that the QG and the parasitic capacitance in the FETs, and or both. So each generation is slightly different, but we see an improvement from one generation to the next. Right now, we're looking at T10 as our newest FET technology. So we're continuing to make improvement in our technology for the FETs. In this chart, I am showing quantitatively what we're seeing going from what we're seeing as the improvement from one generation to the next. So you can see from PT4 to PT6 to PT7, and if we plot a line on it, we're seeing about on average 15% reduction in the figure of merits. So figure of merits is basically a product of RDS(on) and the gate charge. So So the advantage and the benefits is pretty major at 15% of reduction year on year, sorry, generation on generation. And we expect to continue making that improvement, but at some point definitely I think we will reach a limit. But so far we're still able to continue improving our technology with this 15% reduction. Okay, so that's one way to address the higher density. Another way is here what I'm showing is a typical layout example of the voltage regulator to support the Intel CPU. So here you can see that there is some distance from the CPU and the voltage regulator, and that's because of the keep out area that's required for DIMMs. On a typical server board layout, you would have the CPU in the middle and DIMMs on the side, running vertically on both sides of the CPU. So DIMMs have a lot of signals that need to be routed. So the Intel's recommendation is to have a keep out area to run these signal tracing so that they don't get corrupted by the switching noise that's coming from the voltage regulator. So with the keep out in mind, we cannot place our voltage regulator within this area, and we had to place them at some distance away from the CPU. So if you run a parasitic extraction of the board, you can see that in this generation it's a 7-phase design from the Ice Lake CPU. There's about 0.2 milliohms of parasitic resistance between the voltage regulator and the CPU. So and at the maximum current of 394 amps, I2R would tell you that we have about 31 watts of loss just from the parasitic resistance. So this is very significant. Poses a challenge for thermal design on the server. So customers, this is basically the extra power loss that's not needed at all. So in addition to improving the FET technology that we have, another way to increase the power density is actually try to reduce this parasitic resistance. So what can we do? What we can do is to work with inductor vendors to come up with a narrower inductors, and at the same time also consider improving our packaging technology so that we can put the FETs with the same amount of performance in a narrower package, maybe narrower but taller, or narrower or longer. This way we can move our total solution closer to the CPU and reduce this parasitic resistance by about 50% or more, and that translates to much lower loss. So if you add up, this 31 watt loss is probably a total loss that almost a total loss of what we dissipate in the whole VR solution itself. So if we can cut that down by half, that will provide a lot of improvement to the thermal performance of the board, and customers would be able to use lesser cooling technology and drive down their cost. Okay, with that, that's all I have today. And Jason, I think we are ready for Q&A.
Yes, Leo, thank you very much. Let me remind everyone again who's in attendance here, if you have any questions that have come up from the presentation, definitely use your Q&A widget and submit those right now. We got a handful of questions to go through and would love to go through your questions also. So Leo, with that, let's dive in here. First question that I'm seeing is, do you see a limit in your current FET technology to handle the increasing load demand?
Yes, even though right now we're not meeting that limit yet, but I definitely foresee that limit with silicon technology is gonna happen sometime. And people have been saying for years that we're almost at the end of the silicon. We're basically getting diminishing return from a silicon technology, and it's time to move to wide bandgap technologies such as silicon carbide and GaN. So far, we're still able to squeeze out performance gain from our current silicon technology, but we as a company also have investment in a wide bandgap technology as well. So I do foresee that at some point in the future. It's hard to predict when that's going to happen, but definitely at some point in the future, we're going to have to explore another technology.
All right, thank you, Leo. I think this is a really great question here that someone has just submitted to us, and it's about, where do we go? Where do we see ourselves in the next few years? And the question is, when will this increase in current requirements, when is that going to reach a plateau? We go from 5 nanometer to 3, but in that case, we have another 5 or 8 more years for this kind of process. So what do you see for the current requirements reaching a plateau?
I definitely think for the next few years we're still going to continue seeing this current requirement going up, and I am not sure. I think the ASIC and CPU vendors like Intel and AMD are all probably also seeing very similar things as we're seeing with the silicon technology. They're probably also exploring different ways to move away from silicon and into a new material, so that they can keep the same amount of low current with a new material, but still have the performance gain. So I do think that that's going to happen in the future. I don't know when that's going to happen.
Got it.
But
now,
to answer,
sorry, go ahead.
Yeah, but to answer the question, definitely, I think the pitch is going to keep going lower, 3 nanometers, 1 nanometer, and I'm not sure where the limit is right now, but we're definitely going to reach a diminishing return at some point.
Mm-hmm. Absolutely, it'll be interesting to see what that development looks like as we kind of get closer to that point here in the next few years. Now, are you exploring more component integration to reduce solution footprints?
Definitely. So there's still more things that we can integrate, and one example is to integrate the power stage and the inductor. So this work has been going on for some time, either at onsemi or some of our competitors that we have heard, where we're considering. We're working on placing the inductor on top of the power stage so that we can basically reduce that solution footprint by another 50%. Of course, this poses a challenge on the ability to thermally to dissipate the heat from a power stage. So instead of having say a total of 120 millimeters square to where the inductor is placed side by side with the power stage, we're down to just maybe 50 millimeters square. So and while trying to dissipate the same amount of heat in a smaller area is going to be a challenge. So customers doing this kind of study typically would probably have to put a heat sink on top of the inductor. I hope this answers the question.
Yeah, I think so. Another question that we have here, can you operate the power stages at their rated peak current indefinitely?
So the way we rate our power stages in terms of peak current is that we keep the ambient temperature at whatever it takes to operate at that current level, so that the junction temperature does not become destructive. So it really depends on the ambient environment. If you're operating always at room temp, or if you have a cooling technology to keep the case temperature close to close to the ambient temperature, room temperature, then yeah, I can definitely, we can definitely operate at our power stage at the peak current indefinitely. So it's heavily dependent on the ambient environment and the cooling technology. But typically, the way the customers use our power stage is to provide that kind of peak current for just a short amount of time, because that's typically what the CPU requires. And there's a terminology called TDC, which is a thermal design current that each CPU is usually publishes. Sorry, that each CPU vendor publishes for each CPU. So that is the current that we usually design for to operate indefinitely at that current in a typical, say, a server or data center environment. Okay.
Okay, thanks, Leo.
No problem, Jason.
Another question that we have here, this person says they've been hearing a lot about 48-volt technology, and if you can unpack that term for them, what is it exactly? Yeah,
it's a good question. So the traditional server design actually runs off 12 volts. So the input to the power supplies is 12 volts. So as we increase, as the CPU load current increases, that gets translated to the input current of the power supply, which is the 12-volt current. So when the current goes up, that means the server backplane, which the blade cards are plugged into, have to increase as well to cope with the higher input current. And since we know power is V times I, voltage times current, if we increase the voltage from 12 volt to 48 volt, then while keeping the power constant, we can decrease the current that's going through these backplanes. So that's why a few years ago, actually more than a few years ago, it's probably been a decade, where the industry has been exploring the idea of migrating a traditional 12-volt backplane or bus bar to a 48-volt, so that we can keep the input current low and not have to grow the size of the backplane that much. I hope this answers the question.
Yeah, I think so, Leo. I'm seeing another question in here. We're talking about space constraints, size earlier. What about other applications such as AI computing where the space constraints are really tight? Are you developing products for that particular area?
Yes. So the products that we have today can definitely go into AI, and as a matter of fact, we do sell our products into the artificial intelligence market. So there are definitely a lot of ideas floating around. And one of them I just mentioned, which is to place the inductor on top of the power stage. Another one is to, another couple ones are to combine the different phases into a bigger package. So these are several ideas that we're exploring with customers, and I'm afraid I can't talk too much without a confidentiality reason, but there are definitely several ideas to continue integrating the components.
Got that. We'll be excited to know more about that once we're a little bit closer to showtime with all of that stuff. Another question here. We've been talking about where are we at today, where are we going in the future. Where do you see the VR design trends? Where do you think we'll be 5 years from now with that?
5 years from now, right? So I definitely see a lot more integration, like the ones that I've been mentioning, and I do see the trend moving to 48 volt. And part of the initiative to move to 48 volt is not just to reduce it's not just to make it easy on the server backplane design, but it's also to provide a solution to step the 48 volt down to 12 volt that has a very high efficiency. So right now right now the server, most of the server customers are converting from AC voltage to 12 volt through a typical, a very general AC adapter. And if we and there's definitely obviously a lot of losses from there. So some people came up with the idea of doing a 48 volt directly to 1 volt. And in fact, there is a competitor of ours who offers a solution like that. But there's a lot of challenges, and there's a lot of supply risks because there are not that many people doing a design like that. And so I think 5 years from now, it's more likely that we see most customers adopting a 48 volt design such that they step the 48 volt down to 12 and still continue to use today's technology to provide the core voltage to the CPU from 12 volt. So the advantage of doing that is that we can use a very simple design, power technology design, to step the 48 volt down to 12 volt while achieving a very good efficiency, because the 12 volt does not have to be very regulated very well. So we can use something like a switch capacitor circuit to perform that function, and that gets a very good efficiency, then to directly step from 48 volt down to 1. So that's the trend I think we'll be seeing a few years from now.